And as many of you know, it's all about decrease the greenhouse gases and the greenhouse effect. And the HFCs, the current one, are part of that and is contributing quite a lot. In this presentation, we will cover SWEP at a glance, the main drivers for refrigerant change, HFC phase down. I will speak a little bit about PFAS restrictions. We have an application and refrigerant map that I would like to guide you through, a little bit about propane applications. Per will guide you through SWEP refrigerant activities, what we are doing right now. We have some summary and conclusions, and then finally the Q&A. A little bit about SWEP. We are a relatively young company. We were founded 1983 here in Landskrona. And we are a producer of brazed plate heat exchanger, a quite common component in many energy systems. Our headquarters are in Landskrona, and we are part of the Dover company, which is a listed public company in the United States. Currently, we are 1,150 employees worldwide, and we have 5 plants and 22 sales offices in Asia, Europe, and the Americas. So let's start to look what are the main drivers for refrigerant change. We start with Europe. This year, there is a new version of the F-gas regulation. It's named 2024-573. And in this revision, we see an accelerated phase down from 2025 and a complete phase down by 2050. And there are also new bans introduced. The standard EN 378 and the substandards 60335-2-40 and -89, they are quite important since they allow a higher charge of A2L and A3 refrigerants. That means refrigerants that are mildly flammable or flammable. We also see that the prices of HFCs are increasing. And then finally, we see that the proposed PFAS restriction in Europe that might ban HFCs and HFOs. And all these contribute to the change from the legacy refrigerants to new ones. Moving on to the United States. Here we have the AIM Act and the Kigali and Montreal Protocol. AIM Act is actually a proxy of the Kigali Amendment. And this drives the phase down of the production and consumption of HFCs by 85% by 2036. And also here we have bans introduced. Several A2L refrigerants are now listed as acceptable substitutes. And we also have the building codes, the important ones. They were changed 2024, and they allow the use of A2L refrigerants in comfort AC applications. In China, the Kigali Amendment of the Montreal Protocol will drive an 80% phase out by 2044. The regulatory pressure is not very strong in China. The first phase down will happen 2029. But we already today see a direction towards low GWP refrigerants, typically are 2032. And then finally, Japan. They also follow the Kigali Amendment, and they will drive an 85% phase out by 2036. They also have their own local act on fluorocarbons from 2021, and this one promotes an accelerated phase down. I will come back to that shortly and describe the details of that one. Then I would also like to mention that Japan has a long tradition of using natural refrigerants like CO2, especially for tap water heating in the EcoCute systems. If we take a look at the HFC phase down, you can illustrate it in this chart. On the y-axis, we have the percentage phase down of the baseline, which is up here 100%, and it's phased down to 0%. On the x-axis, we have the year, so we can see how it develops over the year. Then the percentage phase down can also be translated to an average GWP. So for example, just above 30%, we have an average GWP of 650, and below 10%, we have an average GWP of 150, and 100% is around 2,200. So the black one here is the old F-gas, and we can see from 2024, it's replaced by the new F-gas, and you can see that it's phasing out HFC in a more accelerated pace compared with the old one. And it's also phasing down it down to 0% compared with the old one that stopped here at around 24, if I remember correctly, or 21. The green one here is US, Japan, and Australia. And we can also see that they are one of the most aggressive in terms of phase down. And this year, they have made a major step in phasing down HFCs. Over here, we have China, South Korea, and Brazil is the blue one, and the red one is China. And we can see that China have the first phase down 2029, and India has the first one 2032. Another way to look at the phase down is to identify what are the phase down for a particular application and what are the bands. And in this chart, I have focused on chillers. I have 3 charts here, one for EU, one for United States, and then one for Japan and Australia. On the y-axis, we have average GWP, and on the x-axis, we have the time, the year. So here is a 10-year horizon on the changes. To the right, we have the refrigerants. The first box is high-pressure refrigerants, where legacy refrigerant is 410A. It has a GWP of 2088. And the right box here is medium pressure refrigerants with the legacy refrigerant of 134A with the GWP of 1430. The green refrigerants are A1, so they are non-flammable. The orange here are A2L, mildly flammable. And then we have A3, which is flammable refrigerants like propane. So let's take a look at in Europe, what's happening there. First of all, we see the blue one. It's the same as in last chart, where we see it's being phased down. We have 2025 here, and then we have next phase down 2027. And 2027 is also an important year because we have two bans being introduced, one for chillers below 12 kilowatts. It's at 150 in GWP. And for larger chillers, there is a ban on refrigerants above 750. So we can see here from 2027, we have these possible refrigerants to use. There are also other refrigerants, but I have selected the most common here to simplify the chart and the discussion. So from a regulatory point of view and bans, only these can be used below 750. But if you have a look to the phase down, you can see that already 2027, there is a phase down to approximately 260 in GWP. So that means in average, it's becoming difficult to use 454B and R32. It's not forbidden, but it drives the emission in the wrong direction. Looking to United States and the AIM Act, we have a big step here, 2029, and there will be a ban introduced from next year, 2025, and it's comfort chillers. They cannot use refrigerant with a GWP above 700. So once again, what you see here is that they can be used from a regulatory point of view. And also looking to the AIM Act, the average is around 600-700 in GWP. So that means that both R32 and 454B are suitable candidates for replacing 410A. Japan and Australia has the same phase down here. But in the case of Japan, and their act on fluorocarbons, they have actually a target of reducing average GWP to 450 by 2030 and then by 2036. And you can see this gap here is actually telling us it's more aggressive. Once again, China will actually have the first regulatory pressure 2029, and the same for India 2032. This is a reference slide, and I saw that Helene comment we will share the slides separately and also the recorded presentation will be shared. So here is a little bit more about F-gas and different applications. I have only spoken about chillers here, but there you can see there are other applications. The same for United States, also more in detail what the limits are, the bans and for each application. So moving on to the PFAS restriction. In Europe, there has been a lot of activities and a lot of discussions regarding PFAS. And in short, it's 5 European countries who have made a proposal for a broad ban at EU level on all PFAS-based substances. And it's the concerns for human health and the environment that drives this proposal. And the breakdown product, TFA, is the main concern here. In Europe, the definition of PFAS is actually any substance containing either a CF2 group or a CF3 group. And when defining PFAS as this, it will also include HFCs and HFOs. And in this box here, we can see what is PFAS classified. but there are a few out of scope. So, for example, R32 is not included in the current definition of PFAS. The timeline for this process is driven by ECHA, or ECHA, is the European Chemicals Agency. And they started already 2020 with preparation, and then 2023, they submitted the restriction proposal. And during 2023, they consulted different companies. Anyone could actually answer a number of questions. And all this feedback is currently being evaluated in different groups driven by ECHA, and it's called opinion development. And somewhere from 2027 to 2029, the decision will be made and also the follow-up. So not before this, there will be a restriction in place. In the case of United States, they also have, from 2021, a PFAS strategic roadmap. But in the case of United States, they have a different definition of PFAS, and it's not 100% clear, but one definition is that they specify substances subject to restrictions typically contain at least 2 fully fluorinated carbon atoms. So with that definition, they are excluding fluorinated refrigerants. So the European case and the the US case is very different. At SWEP, we have this application and refrigerant map. It's a way of looking into different applications. And if we start from the left column here, we have our different segments. So air condition, we have residential heating, we have industrial applications, we have refrigeration, and we have clean energy. Then we have different applications within each segment. We have the BPHE use, we have the legacy refrigerant, we have what we think will be used short-term and long-term, and here are the drivers for each application. And it's a quite busy slide, so I would like to focus here on 2 applications. One is the scroll chillers, and the other one is air-to-water heat pump. Starting with the scroll chiller, in this application, they use the BPHE as evaporator and/or condenser. The legacy refrigerant is typically 410A. Right now, and for another year, we believe there will be a number of refrigerants in parallel. Some markets will continue with 410A. Some are migrating to R32. We have 454B as a candidate, and then we have R290, which is the same as propane. Moving on to long term, let's say 2025 and forward, we see that 410A will still be used in China, although we see indications that they are looking into, or at least our customers are looking into R32 as a replacement to 410A. But there is no regulatory pressure on China to switch, actually. In the rest of APAC, R32 is the dominant. There might be still some use in Europe as well. 454B will be the default refrigerant in the US. It will also exist in Europe. And we see a gradual change to propane in Europe, especially for smaller capacities. And once again, it's AMAC, it's the F-gas and Kigali, and together with the standard 378, that drives this change. Going to the air-to-water heat pump, typically those systems are using the BPHE as a condenser. Evaporator is within bracket because there is a defrost cycle where it's used as evaporator. Up to now, 410A has been the most popular, is still being used. But in Europe, and this is a typical European application, we see that currently R32 and propane are very popular here. And long term, it looks like propane is becoming the most popular refrigerant, especially for the monoblock design principle, where you have the full refrigerant system outdoors. Once again, it's the F-gas and it's EN 378 that is allowing this change. If we have a look at propane applications, here it's very important to look into the refrigerant charge. That is, how much refrigerant does the system contain? And if it's below 152 grams, you can use it without any safety measurements. It's handled as any refrigerant. And this is typically used for small supermarket display units below typically 1 kilowatt. And I have a picture here. And the standard handling this is 60335-2-89. And here our heat exchangers are used as condensers sometimes. Quite often they are also air-cooled. If we go up one step to larger supermarket display units and typically water loop, they use our heat exchanger as condenser and is -2-89 standard that is regulating it. And you can see one example here is a rather big display case. And on the top of this display case, there are one or several condensing units, and each circuit is below half a kilo of refrigerant. So you can have several circuits, and if they add to something bigger than this, it's not really a problem. It should be below half a kilo to follow the standard. Then we have the air-to-water heat pumps. Again, very popular in Europe. It allows up to 5 kilos of refrigerant, propane, and it starts being used at 1.5. And it's regulated by the standard 60335-2-40. And here is an example from Weiland here. And this is a monoblock where you have the full refrigerant circuit outdoors, and the radiator water is pumped from the building to the heat pump and then back into the building. Finally, the air-cooled chiller or heat pump. This is regulated by EN 378. And typically, it's air-cooled chillers and heat pumps. And depending where it's placed, it will allow different charges. So a very typical is that if it's installed in a public access, it can be beside a building which is accessible to the public or on the roof. It's placed outdoors. So in this case, you can have up to 5 kilos per circuit in this chiller. So that means we see quite often that the OEMs are designing systems with 2 circuits, and they can also be in modular design. So could place a number of modules to build up the capacity necessary for the building. And if you go to restricted access and outdoors, there is actually no limit on the refrigerant charge according to 378. Here is another reference slide, is the legacy refrigerants here. And for each block here, you can compare, for example, if you have 410A, you can see that 454B has slightly higher COP, but slightly lower capacity. So it's a reference slide that you can use for later. So with this slide, I will leave the word over to Per, who will guide you through our refrigerant activities at SWEP.
Yes. Thank you, Eric, and hello, everyone. I hope you find the webinar interesting so far. And now I will take the opportunity to talk a bit about SWEP's activities around refrigerants. And even if SWEP heat exchangers, the BPHEs, are compatible with the refrigerants that have been mentioned in this webinar, there are some combinations of refrigerants and BPHEs that will perform better than others. So in order to be as accurate as possible when we do the design of our heat exchangers, our heat transfer laboratory will continuously test and validate our products. And they do that to ensure we get the best possible performance and prediction accuracy in our selection softwares. All BPHEs at SWEP go through standardized thermal and hydraulic testing, and these to ensure a good performance modeling base. But then for specific refrigerants, we want to further fine-tune the accuracy. So in some applications and for some refrigerants, we also do condenser and evaporator tests that are done in a very standardized way, so standard chiller and standard heat pump conditions normally. And there are several rigs in the lab that we have today, so we have the possibility to test with many of the low-GWP refrigerants that has been mentioned now today. Latest years, we have tested off our product portfolio with several refrigerants, such as R32, 454B, and also propane. So the evaporators and condensers are tested with the different refrigerants, and the data from these tests are then ultimately used to calibrate the calculation models in our selection softwares. And on this slide, you will see two pictures, and the top one is a screenshot from our online version of the selection software, which we call Determex, and the bottom one is from the desktop version, which we call SSP G8. They both have the same calculation basis, so when we update performance for a product based on a test, it will be appearing in both of the versions at the same time. Can move on to the next slide, where we'll have a deep dive into our new propane rig. So SWEP has validated an optimized product with propane for more than 5 years now. And we started with this small test rig that was big enough to measure the performance in our small and medium-sized braze plate heat exchanger products successfully. But since this year, we are also live with a larger test rig, which is reaching up to 160 kilowatts. And 160 kilowatts may sound small to some, but it is actually large enough to accurately test even our largest two-phase products that we sell. And that is since the nature of the VPG as a plate heat exchanger, you can scale the capacity by adding plates, obviously. So by testing a slightly smaller plate pack at a lower capacity, you can always scale that up to a larger size, which is helping us a lot when evaluating products. The test that we do here will tell us if we need to make any adjustments to the calculation models that we have today in our large and extra large products with propane. And on the last slide that I wanted to show, which is this one, I tried to visualize some of our products. We have more products than this, but just to give you a brief view on what we offer. We have some here that are suitable to use with these medium and long-term refrigerants that we have talked about. So if we start on the lower capacities, we have what we call the S range, so the small range, and the BPHEs here typically used in smaller residential heat pumps and economizers. So like Eric mentioned before, propane condenser is one thing that you can provide here, but we have also evaluated this product range heavily with for R32 and 454B. So I think we have tested basically all products we have for that matter with those refrigerants. To mention some, we have the B8LAS, which is a good propane condenser, and we also have the 8 double wall, which is quite recently launched by us. It's a small double wall unit that can meet some additional requirements when operating with propane, as it is using a double wall feature. Then if we are moving up on the capacity ladder, we have the medium range, which features typically residential heat pump condensers as well and chiller evaporators, but at a larger capacity, maybe even into commercial units. Also here we have a good coverage with R32, 454B and propane. Product worth mentioning is the 22AS, which is an R290, so propane optimized heat exchanger. It is functioning very well with propane, both as evaporator and condenser, so very suitable for reversible performance. And if we then look at the larger capacities, we have the 190 and the D190 versions that are recently launched by us. The D190 is the smallest dual that we are offering. Thinking about propane and the limitation per circuit, the D190 can be a good choice for keeping down refrigerant charge and still not going too large in capacity with propane. So this is typically the products that we are testing off right now in our testing campaign with the new propane rig that we are having. But since the legacy products that we have here have been developed mainly for high pressure refrigerants such as 410A and R32, they are naturally functioning very well with 454B and R32 as well. At the bottom here, I also wanted to introduce our CO2, so carbon dioxide heat exchangers. And when you're operating with CO2, you normally have a quite high pressure. So the 4 products that you're seeing down there, they are rated at 140 bar. And they are together covering an operation range from very few kilowatts up to close to 700. New product there is the 285, which is recently launched by SWEP. So very well suitable for larger gas cooler systems where you could use CO2. We also have an evaporator, which is basically the 185 that we can equip with a distribution device, making it functioning better for evaporator duties. And that is something we are launching at the moment, pretty much. With that said, I will hand over the word to Eric again for a summary.
Thank you, Per. So the summary and a few conclusions. In Europe, we have the steepest HFC phase down. Our take is that the medium GWP refrigerants like R32 and 454B, they will be more difficult to use in Europe the coming years. I talked about the phase down 2025 and 2027. We see that propane, it's a long-term solution for several applications, and already now in air source heat pumps is becoming the preferred choice for our customers. We also see it's being used more and more in air-cooled scroll chillers, and then it has been used for some time in commercial refrigeration as well. In the United States, the AIM Act and the Kigali regulation had a significant phase down 2024. We also see the revised building codes are helping to use A2L refrigerants. And our take on new chillers is that 410A and 134A, they are banned from next year. And we think they will most likely be replaced by 454B and R513A. In APAC, we see that China, their phase down is initiated in 2029. So 410A can be used for the domestic market until 2029, but we also see that R32 is gaining popularity. And then finally, Japan's Act on Fluorocarbon, they target an average GWP of 450 by 2030 and below 10 by 2036. So quite an aggressive phase down by Japan. A little bit about our tools and resources. We have links here. We have the SSP calculation software and the Determex calculation software. They differ that the SSP is a desktop software while the Determex is a web-based. Then we also have a X-reference replacement tool. So if you have a heat exchanger that you need to replace, and it's not done by SWEP, you can convert it to a SWEP product with this tool. And then, of course, you can contact me or Per if you have any questions, and also local support. We are quite well spread in the world, so there is normally a local representative in many countries. With that, we conclude with the Q&A. So once again, please write your question in the meeting chat and we will answer them.